Swayam Prabha. Digital India. Educated India.
We were in the business of finding the forced response of a linear system, in particular a first order RC circuit to a sinusoidal signal, okay, which can in general be represented as cos omega t plus phi. That's a sinusoid of frequency omega and some amplitude Vp, okay. So this is the general form we will use. So for instance, if the input is sin omega t, we will still think of it as Vp cos omega t minus pi by 2. Okay, that's just for uniformity. Later we will see that there are lots of shortcuts we use. We won't go through all these steps that we did, putting exponential there and then doing all those things. Okay. So in the general scheme we came up with was that if this is fed, although we took the example of an RC circuit, a linear system with real coefficients, you will get some output. Okay, I'll just call it a response to Vp cos omega t plus phi, and if I had sine here, I would get something else which is a response to Vp sine omega t plus phi. We also know that the force response, by the way, I am talking here only of the force response of the steady state response. Okay, force response to Vp sine omega t plus phi. Then in this case what we can do is to superpose these two inputs, multiplying this by 1 and this by j, which is square root of minus 1. Okay, and when we do that, my input becomes Vp exponential j omega t plus phi. Okay, and it of course goes into the same linear system with real coefficients. Okay, clearly now a linear system obeys superposition as far as the force response is concerned. So the response would be this times j plus that times 1. Okay, the reason for doing that is that the force response to an exponential input is very easy to calculate. We've already done that. What is the force response to an exponential input? It is the same exponential scaled by some number, and that number depends on the circuit, components in the circuit. Okay, so the point is that this is easy to calculate. Okay, so we do that, but what we are really interested in is the response to Vp times cos omega t plus phi. Okay, that's the signal we are feeding in. Now, because the linear system had only real coefficients, the only place where you get this square root of minus 1 or the j, the imaginary part in the whole picture, is because you multiplied it here. Okay, so to go back to this, you take the real part. Okay, so lots of analysis is based on this. In fact, after a while, it's quite common, especially in communication systems and so on, to talk only in this complex exponential j omega t. You won't even hear cos and sine, but you should understand what it means though. Okay, what we are really calculating here is the response to Vp times cos omega t plus phi, and that can be obtained by calculating the response to Vp exponential j omega t plus phi and taking the real part. Okay, the reason this works is because the linear system has real coefficients. If it had complex coefficients, things could get mixed up. Okay, there are actually systems like that which we won't go into at all. But alright, so this j, which is square root of minus 1, kind of keeps the two things separate. You can combine them into exponential, but they are still separated as real and imaginary parts. Okay. And for our particular circuit, what did we get? If I apply Vs here, I'll get some response. Okay. So if Vs was Vp exponential St, the forced response was, what was it? Right. So clearly Vp exponential j omega t plus phi, which is the same as Vp exponential j phi exponential j omega t. Okay. So this whole thing is multiplying exponential j omega t. So this part is like that. Okay. So what's the response now? Vp exponential j phi 1 plus j omega cr exponential j omega t. Okay. Or I could put these two things together anyway, which is also Vp exponential j omega t plus phi, which is the original exponential divided by some complex number. Okay. And finally, Vp cos omega t plus phi, what is the response? The real part of this. Okay. And what is that? Many ways to do it. First of all, assume you are already pretty comfortable with calculations involving complex numbers. There are two forms of complex numbers. This is known as the rectangular form, where you give the x and y coordinates of the complex number, or the polar form, which gives you the amplitude and the argument or the angle. Okay. Now, both representations are useful. Clearly, this is more convenient for adding complex numbers. This is more convenient for multiplying complex numbers. Okay. So if I use this here, what do I have? 1 by 1 plus j omega cr. What is the amplitude of this? That is the amplitude, and the argument is minus tan inverse omega cr. Okay, there are so many ways of doing it, or you rationalize so that you get the real denominator and then a complex numerator and so on. Okay, so finally the response to this turns out to be Vp by square root of 1 plus omega cr square and cos of omega t plus phi minus tan inverse omega cr. Okay, so you apply a sinusoid to a linear system. What you get out is a sinusoid of exactly the same frequency. The amplitude will be changed and the phase will be changed. How much the amplitude will be changed and how much the phase will be changed depend on the circuit. Okay, so this is the amount of phase change, right? And this is the factor by which the amplitude is changed. So that clearly depends on circuit as well as frequency. Okay, so you can also, once you have capacitors in the picture or inductors, you can have frequency selective circuits, that is, circuits which behave differently at different frequencies. Clearly, you can see from this expression itself that if omega is very large, the amplitude of the output will be very small, and if omega is very small, the amplitude is the same as the input. Okay, and very small is compared to 1 by RC. Okay, so if omega CR is much smaller than 1, the output amplitude is Vp. If it's much more than 1, it's inversely proportional to omega. Okay, so we will look at these things later when we discuss sinusoidal steady state response in more detail. This is known as the sinusoidal steady state response because, I mean, it's the steady state response to a sinusoidal input. Okay.